I'm Eli Wintersheet, and this is Lab 3, Magnetic Field of a Bar Magnet. This lab focuses on the measurement of a magnetic field from a magnetic dipole. The system is measured using a magnetometer in an iPhone and is then modeled in GlowScript. The specific iPhone used during this lab was an iPhone 12 Pro, and experimental results were put in from that magnetometer measurement into an analysis script in Excel to find the average dipole moment, mu. The formula used can be seen on this slide here. The first we have is the magnitude of the dipole on axis, and this is an approximation. And then we have the same formula, but this is using the distance dependence n, which is found using the Excel script. And then we have the general magnetic field of a dipole, so not on axis and not perpendicular to the axis. So some quick data and observations. The magnetometer found in the iPhone was about 1 centimeter in and down from the top left corner. And then the approximated n value using this Excel script, everything was put in here and it calculated it automatically. The n value was negative 1.243, and the lnk value was negative 12.4. And so once these values were plugged into the general dipole equation based on the distance the second formula I showed on there, mu was found to be 2.471, so that is the dipole moment. And so some observations: when the magnetometer was far away from the magnet, it measured a near zero magnetic field, and as the magnetometer moves closer to the magnet, the x component increases. And this can be expected because we're getting much closer to the source of the magnetic field. So now when we look over at the GlowScript, we can see that the magnetic dipole moment is input right here, and we have our function that uses the general dipole formula, and that's called below. And we have our arrow scale just so that we can actually see the arrows. And the most accurate distance that I found was 30 centimeters away. This on here you can see that's right about where it lines up with the line of best fit. It gets generally less accurate right here, and then a little more accurate right there. So I'll take a look at a couple different distances. These are just observation locations, and creating the arrows. And then we looked at the 45 degree, so we can take a look at how this looks at 30 centimeters away. We can see the on-axis is modeled in orange, and that's very close to our measured 20 micro Teslas. And then the perpendicular is modeled in this cyan color, and that is that's not something that we measured, but I'm sure that that is a good estimate. And then here's our 45 degree arrow, which we measured. The distance measured was very similar to 30 centimeters, and the magnitude of this is about half of the expected measured one. So I'll look at that in just a second. So now when we go back and we change the distance to, say, one of our other values that we found, about 4.8 centimeters away, we should expect to get something in the vicinity of 220 microteslas, but here we see that's a few more orders of magnitude off. So obviously this script is not quite the most accurate. Yeah, it's not the best, but it works as you get farther away. So now when we look at the what if questions, what if we hadn't oriented our experiment to compensate for magnetic north, and instead just had it some arbitrary angle with respect to the Earth's magnetic field? And the answer is we would just get some weird sine and cosine of the birth value within our x and y, and we would have to know what that angle was to be able to separate it out. So it would just cause a lot of headache and extra steps that we don't exactly have the information to deal with. And then if we were to run two identical magnets together end to end, what would happen? Basically, we just made a bigger magnet, so I assume that the magnetic dipole increases, I am not a physicist, so I am not the leading expert on magnets, so I don't know. Magnet kind of go burr, you know? Thank you for watching this awful, awful lab. I love you.